Good evening to everybody. Let's wait for 5 more minutes and then we'll get it started. There are a lot of participants who are yet to join. Let's wait for it. Couple of more minutes and then we'll get it started. All right, everybody, let's get started with our today's proceeding. Yesterday, we have finished our fundamentals part. We have discussed about our 4 core libraries and packages, which includes NumPy, Pandas, Matplotlib, Seaborn. Let me give you a quick revision of what we have done yesterday as an EDA topic. Okay, so in our yesterday's session, we have discussed about I've taken a new data set, which is Big Mart. I don't think so. We have done this. Mhm. Okay. Actually, we have done this particular example. Okay. Here we go. This is how the things are done. This is what we have done. We have discussed first about the matplotlib, which is basically one of the library in Python that support fundamental plots, bar graph, line chart, okay, histogram plot, pie chart, scatter plot. These are your fundamentals. Seaborn is for complex plots. They come with built-in themes, color palettes, styles for attractive chart, specialized in statistical plot like distribution plot, heat map, pair plot, variant plot, etc. Now that we have discussed it, let me give you a quick idea about some of the statistical terminologies that we have discussed yesterday. Let's have a deeper dive into that as well. One of the important term in the statistical part is to know that what do you mean by a data set? What do you mean by normal distribution? Okay, and if your data is not normally distributed, then it is gonna be static. It is gonna be represented as skewed data. So let me show you. Okay, now in the district, no, this is not. This is the one. All right. So look at here. If your data is represented as a curve shape, there are three possibilities, or there are three possible outcomes here which are there. One is your data will be having a long tail towards the positive side, and the majority of the data will be closer towards the zero value, or you can say closer towards one side, and it will have skewed, and it will be skewed towards the right hand side. Next is normal distribution, which is basically symmetrical about the mean. And in normal distribution scenario, which is symmetrical about the mean, you can clearly see that 50% of the data is on the left hand side, and 50% of the data is on the right hand side. This indicates the data is having this is this is something which shows that data is skewed. It is not skewed, but it is splitted or symmetrical about the mean. This is one of the key characteristics of a normally distributed data. It is a skewed, a normally distributed data, which is a bell-shaped curve data. It will be symmetrical about the mean. And one more thing you need to remember is that your mean, median, and mode, all three will fall in the same line. Next is negative skewness. In the negative skewness, the tail will be towards the negative direction. As you can see, the long tail is towards the negative direction. In this, majority of the data or major distribution of the data will be closer towards the negative direction, whereas in this case, the major distribution of the data will be towards the positive direction. In this case, mean will be greater than median, will be greater than mode, whereas in this case, your mode will be greater than median and median will be greater than mean. This is a skewness positive, this is skewness negative. So three type of distribution is there that you can show it. So we have splitted the plot. This is also your distribution plot. As you can see that there is a skewness here. So how to identify? One way to identify that if there is a skewness in the data is through this plot. Other method is you can simply select the value and you can select that column and you can run it as dot skew function and you will get the response. Histogram also is having the capability to show that the distribution is skewed or distribution is positive, negative. Let's just check it. Okay, so you can clearly see that it is showing the skewness. The price is showing the skewness of positive value, whereas okay, this is also showing the positive value only, both of them, as the tail is towards the positive direction. So if you will calculate their skew value, they will show the same positive skewness. So if I have to just find out if there is a positive skewness or negative skewness, you can simply let's take here the data set and we have engine size dot skew and it will return you that it is positive. Higher the value, longer will be the tail. As it will become closer and closer towards the zero side, we will say that the data is normally distributed. Okay. Next thing. Okay, if your data is if your data is normally distributed, so imagine that a data shows a normally distributed curve. Then in that case, these are the criteria which will be set up, and that is, first of all, the mean will be dividing your distribution into two halves. Next, between first standard deviation, okay, between the range of first standard deviation, 68% of the overall data will fall within this range. This is an empirical rule that applies to a normal distributed data. 95% of the overall data samples falls within the range of second standard deviation, and that is between mu minus 2 sigma to mu plus 2 sigma. Similarly, mu minus 3 sigma to mu plus 3 sigma. Of approximately 99.5% of the overall sample data falls within the same within this third standard deviation range. Range means the difference between minimum value and the maximum value. So this applies to only and only if your data is normally distributed. Otherwise, this is not valid. This is not valid to any skewed data. Similar to skewness, there is one more distribution which is there, and that is kurtosis. Kurtosis measure the tailed tailness of the distribution, whether it is having a heavy tail or whether it is having a flatter peak and a light tail. So whether it is having heavy tail or whether it is having light tail, three type of possibilities there. Mesokurtic means your kurtosis is normally distributed. When your data is normally distributed, then it is considered as mesokurtic. Next, leptokurtic. When you have a sharp peak and heavy tail distribution, there will be a one long peak and the tail will be heavy. That means long tail. The sharp peak, long tail, leptokurtic, and plitokurtic is there when you have a light tail and flatter peak, which will be, and then the criteria is very simple. Criteria is when this will be compared with the normally distributed curve. If the peak is greater than the peak of the normally distributed curve, you can say that it is having extreme outliers. Sorry, it will have extreme outliers due to heavy tail and one sharp peak. Whereas the light tail and flatter peak will be below. So the peak will be below than the, if your peak is below the normally distributed curve, then it is plitokurtic. If your peak is greater or more sharper than your normally distributed curve, then it is called as leptokurtic. Let me represent it similar to skewness. You can also check for the presence of kurtosis. It is coming up as greater than 3. So you can see very sharp peak is there. If your data will be normally distributed, it will be closer towards the 3 value. If the peak would have been flatter or broad, flatter like this, then this value would have been in the negative scale or below than 3. Next important thing to note down is how to identify the outliers in the data set. And what is the IQR part. We have not discussed that part in depth yesterday. Let's discuss it, how to identify the outliers. So point number, in all the discussions that we had in the plot, let's talk about the IQR, and or we can say this is about quartiles and outliers. So how to identify the outliers? It is important for us to indicate to discuss this. So box plot is one of the best plot to identify the presence of outlier in the data set. Let's replace it by engine dash size, and so this is having these many outliers present. So pretty less in number, no problem. We have to just identify it. Okay. So in order to identify the outliers, what we can do is, first of all, what is this point? This is your quartile 1, or called as Q1. This is quartile 1. And in order to calculate the quartile one, you write like this. Okay, it is giving you the suggestions. You have to write data frame with the column name dot quantile and 25th percentile. So Q1 is 25th percentile. Next is Q2. Q2 is 50th percentile, which is also known as median. And next is 75th percentile, which is your third Q3. So we have got Q1, Q3, followed by is your IQR, that is represented by Q3 minus Q1. So it gives you IQR. And what is IQR? IQR is this value. This is start of the box is your Q1 value, whereas the end of the box is your Q3 value. And IQR returns you 44. That's the range between this value and this value. Okay. Now, what about these line? They are basically they are called as upper bound and lower bound. So, or upper limit and lower limit. So first, let's identify the lower limit. This is represented by Q1 minus 1.5 times of IQR. Similarly, what is your upper limit? This is represented as Q3 plus 1.5 times of IQR. So we go ahead with my lower limit and we go ahead with my upper limit. So we got here my upper limit value, which is 31. So any value of the engine size which is lower than 31 is a outlier, or any value which is greater than 207, they are also outlier. So these are the values which are greater than 207. Okay, so these are some important terms. Quartiles, which is your statistical term. 25th percentile is your quartile 1. As this is basically nothing but you are dividing after every quarter. This is your first quarter, that is 25th percentile. Then this is your second quarter, which is your quartile 2 as 50th percentile. And then we have got Q3, which is your third quartile. So you identify the every quarter, and the last is your upper limit and lower limit. That's not your 100th percentile, but that is your that is indicating your last limit, upper limit and lower limit actually. Okay, are we done? Any question? So these are some important things that you can Any questions to ask? Okay, about the correlation I have already discussed. Correlation is the measure of linear relationship between two variable. If the correlation comes out to be closer towards +1 or -1, that means there it will indicate that there is some correlation between them. And if the correlation is closer towards 0, it will indicate there is no linear relationship between both. Now we will start with our first algorithm. Achha, by the way, you all know how to what all statistical terms are there, right? Standard deviation and all. Hopefully, you know what is the meaning of standard deviation, what is the meaning of mean, median, and mode. All these things. I hope you all don't know, don't want me to discuss, right? Those are all pretty fundamental statistical terms. So expect that everybody knows about it. Let me start with the first algorithm straight away, which is linear regression. And let's continue. Let me start with our linear regression model. Let's start with our linear regression model. First of all, we will learn about in this the definition part. What is the meaning of a linear regression model? We'll discuss about it. Further, we'll learn about what is the definition. It's about the example problem statement also. We'll discuss about it. Followed by assumptions of the linear regression, which is very important because you need to understand linear regression cannot be implemented everywhere. Then we'll be creating a mathematical equation, multiple linear regression. There are different type of linear regression model which are available, so we'll also talk about that. Model hypothesis equation, this error function, cost function, etc. We'll discuss that. Gradient descent, model optimizer, and how do we train the model, training and its evaluation metric, followed by a very important term called as R squared value, adjusted R squared value. These are the things which we'll be able to identify. So first, let's start with the introduction part. Now we have discussed it in the day one of our learning session that ML is divided into three categories, right? Out of that, let's just focus on two categories as of now. One is supervised. The other one is unsupervised. We have got a supervised learning model. Now this supervised machine learning is further divided into two categories. If your label is there, we say that it is supervised, and when you are having no label, then it is unsupervised. So you need to first see the data set. When you will see the data set here, when you will see the data set, and if the data set is having a label target, you call it as that it is a supervised learning. But when in which scenario it will be a supervised linear regression model? So the nature of the label should be continuous. You just say that your label is continuous. So linear regression is a supervised machine learning algorithm where the predicted output or the y hat is continuous and it has got a constant slope. It is used to predict values within a continuous range. For example, sales, price, rather than trying to classify, you're trying to classify them into categories. Because in this case, the label will be not a categorical value, but label will be continuous in nature. Remember, label will be continuous. Continuous means it could be any value like price. Price is a continuous value. Now, there are few important things which it will tell you about the data set. Linear regression is very good to answer the following question. It will show is there any relationship between the two variables, which feature or variable contributes the most in predicting the target value. So which feature or variable here will be contributing the most? Let's continue with the next part. How strong is the relationship between the input variables and output variables? This is also you're able to identify. How accurately we can estimate the effect of each variable. Next is this is your linear relationship which is able to find it. Now one more thing you need to remember that we are trying to establish a linear relationship between y and x. Next, linear regression is a statistical tool for modeling the relationship between a scalar dependent variable . is a scalar dependent variable y and one or more explanatory variable or independent variable which is denoted by or represented by x. In this case, we are trying to establish the linear relationship. This is your dependent variable. This is your dependent variable. We have got a dependent variable. Then we have got x value. This is your beta naught that represents coefficient of x. Sorry, coefficient. This is your intercept value. You can rather say this is your intercept value. Then we have got beta 1, which is coefficient of x value. X is your input data. This is your input data. So pretty simple. What are we trying to do is we are trying to establish a linear relationship between the dependent variable and an independent variable. This input data is known as independent variable. Now just remember this term independent variable. This will be useful when we'll be moving ahead further. So linear regression, if I have to summarize, this is a statistical model which is basically models here scalar dependent variable, and we are trying to establish a linear relationship, okay, between scalar dependent variable y and scalar independent variable x. This x value could be one or more, and for every x value there will be a coefficient value. Like for x, there will be. So in this case, this is very simple equation, okay, and in this case your y should be of continuous type, and x, if it is continuous, then it will able to fit it better. Like for example, a very simple analogy or simple example or the simple problem statement that linear regression can solve is when you have provided with the speed of the vehicle, the speed of the car, and you have been provided with the distance traveled. Both the scenarios are given. What you can do is you can establish linear relationship between both, between the distance traveled and the speed of the vehicle. So we have the speed, which is represented as x, and we have the distance, which is represented as y. And let's establish the relationship, which is y equals to beta naught plus beta 1 into x. Here in this case, y is represented as distance traveled, which is equals to beta naught plus beta 1 into speed of the vehicle. This is how they are represented. We can map the distance traveled to the coefficient value plus beta 1 into the speed of the vehicle, and it's done. Okay, now let's move ahead. So you can see that it is very simple. As the speed of the vehicle is increasing, distance travel will also increase. So there is a high chance that there will be a linear relationship between both. Hence, it's perfect for implementing it. Now moving ahead. This is very important. You need to remember that the assumption is important. That's where you can see that we need to remember, we need to provide the assumption of the linear regression model. Okay, as you observe in this case, in the assumption part, we assume that the residual have normal distribution. Residual means the error part. Okay, or you can also compare here y minus y hat. When you compare here y minus y hat, that is actual value minus predicted value. This is the actual real value and this is predicted value. When you compare both, it returns residual, and and when you make a plot of this residual, they will be represented as normal distribution for the respective dependent variable value. Now, a normally distributed data is balanced, bell-shaped curve with one peak and two tail. And most importantly, just to give you one more idea, then a normally distributed curve will be symmetrical about the mean. It's symmetrical about the mean. More often, one more thing you can also say is that your mean, median, and mode, all three value will fall at the same point. These are the important. This is your important point about the normal distribution. Now, most importantly, linear regression assumes that your residual will be normally distributed. That means when you will make a plot of error curve, it will be represented as normal distributed curve. How to identify, how to examine it? You can make a plot of residuals by using histogram, box plot, and QQ plot, which is basically one of the important metric, important plot. It's known as quantile plot. So quantile plot is there, which will be representing it as no, which will be identifying it as a normally distributed curve. Next is assumption number two. Assumption number two, one of the important thing is that when you will make a plot of error or residual with respect to the predicted value, it will show a homoscedasticity. It will show homoscedasticity. Okay, what do you mean by homoscedasticity? Homoscedasticity means homo means similar value, and we are basically talking about the variance, homogeneous variance. As you see in this case, when you will make a plot between the predicted value and the residual value, it is represented as homogeneous. All are homogeneous here. We have got homogeneous. Now, if your data is not homogeneous, then it will be heterogeneous. So, if it fails to follow this, there is a plot between actual value and residual does not scatter itself in such a way that it will show the equal variance. Rather, it shows something like this: unequal variance. Here, here the data is having less spread, so your variance is very less, or standard deviation will be less. Whereas in this case, the spread is high, so the variance will be higher here. In this case, variance will be on the higher side, and here the variance will be on the lower side. So we have on one side variance as low, whereas on the other side we have got variance as high value. All right. So if this is the scenario, then we can clearly say that your sample data does not follow a uniform variance, but it follows heterogeneous variance. And this is if your plot between residual and predicted value is like this, then your linear regression model will fail to predict your output perfectly. So these are your assumption. That means linear regression will fit properly when these criteria are fulfilled. It applies it uh, it applies the model, or it applies to the data set assuming these scenarios. If they are not fulfilled, or if it fails to fulfill this, then the model will obviously This is clear. Assumption number 3, linearity. The independent variable x, and it should be linearly dependent on the dependent variable y. This is very much important. If you are implementing a linear regression model, you need to understand that there has to be sign of linearity between x and y. X and y must show a sign of linearity here. Okay. Next, relationship between the variables should be linear, or best represented by the straight line. That's how it is. Next, label. Now this is very important again. The target should also show the sign of normality. That means the label should be also normally distributed. Again, the same examination you have to do, quantile plot. Quantile plot. There is QQ plot and residual. This is your label that shows normally distributed curve. The probability distribution of the output should show the normal distribution curve. Already I showed you what you mean by normal distribution curve. Next and one of the important thing is that remember always in the definition it is mentioned that it is a linear relationship between it is a linear regression model establishes a linear relationship between scalar dependent variable and scalar independent variable. Scalar means numerical, right? So if we say that the variables are independent, which indicates that there has to be no high correlation or no correlation between variables input variables. This is our assumption. Now, how to find out if there is a multi-collinearity between the features? So for that, you run a statistical test. You perform a statistical. You implement a statistical function which is called as variance inflation factor, and if this variance inflation factor is high, we say that the independent variables are no more independent. There is a dependency. There is a collinearity, a high collinearity between both. Sorry, not collinearity, correlation between them. But if your values are independent, so their values would be fairly less. So we can say that. So you see that we have got this correlation value. This is expected to be low value between them. But correlation is not the correct metric only to find if they are dependent or not. Better than that, to find if there is multi-collinearity between the features, which indicates that high correlation between the features, we just run this, we just calculate VIF value. If VIF value comes out to be higher between features, we say that they are dependent, and we have to remove one of them. Okay, one of the variable has to be go. So you can also find out it through the correlation matrix as well. But the best one is VIF part, so we'll check it. These are your 5 prime assumptions. Quickly giving you an overview. So if you have missed out, first assumption about the linear regression model is that it should show normal distribution curve. Assumption number 2 is there has to be homogeneous. variance between predicted value and residual. There has to be linearity between the independent variable and independent variable. Next, the label is normally distributed, and no multi-collinearity between the features of between the independent variables. There are other assumptions as well, but they are not that important. Like we expect that the residual will be mean, their mean will be 0. There should be little or no autocorrelation, and all independent variables are uncorrelated with the error term. This is all we need to expect. Okay, so what an important thing. Now let's go ahead with regression discussion. Regression analysis is used to predict the value of a dependent variable based on the value of at least one independent variable, which explains the impact of changes in an independent variable on the dependent variable. So we predict the value of a dependent variable based on the value of at least one independent variable. So they explain you the impact of changes in a dependent variable on the independent variable. The dependent variable is the variable that we wish to explain, and the independent variable is the variable that is used to explain the dependent variable part. Okay. We have taken this example, equation and all we already know. Let's take this part. So there are two versions of linear regression. One is simple linear regression, and the other one is multiple linear regression. Now more realistic is multiple linear regression because you will see many input independent variables to explain the dependent variable. Dependent variable is, let's say, house price. The price of the house is represented as y, which is explained by or given by beta naught plus, we take here beta 1. X1 is your square feet area plus beta 2 into, we have got a square feet area. Next one is number of rooms followed by beta 3, which is so we have got a square feet area, we have got number of rooms followed by your B3 value, beta 3 value, and in this beta 3 value we take let's say number of washrooms plus beta, let's say we write and go for beta n, which will be latitude bn minus 1 and bn will be longitude. That will be indicating your equation. So n number of features are possible and they are represented like this. So they all will combine together. These are all your independent features. This area of the house, number of rooms in the house, number of washrooms in the house, latitude, longitude of the house. They all are independent variables, and combined together they will give you they will help you to explain the price of the house. Okay, so that's what this beta naught plus beta 1 into x1, beta 2 into x2, beta 3 into x3 goes up to beta n into xn explains. Now there are four type of relationship is possible. One could be that between x and y, this is your x value, which is your input, and this is your dependent variable. Between your x and y, there could be a positive linear relationship. Next is the relationship is not linear. If it is not linear, then linear regression model will fail to explain you. Then you then you use polynomial here. Polynomial linear regression. So relationship will be not linear. Next is negative linear relationship. Okay, which means that with increase in x, y will decrease. In this case, the explanation could be like this: y equals to beta naught plus beta 1 into x1 square plus beta n into, sorry, beta 2 into x2 square, like that. Similarly, we can have a possibility of zero correlation. And zero correlation means no relationship between x and y. Okay, so we have got zero correlation. All right, that's how the things work. Now let's go ahead and let's talk about the algorithm. This is how the algorithm looks like. Now remember that this is known as hypothesis equation. What is hypothesis equation? Hypothesis equation this is basically we have an algorithm hypothesis which is represented like this, and to find the parameters we need to minimize the least square or sum of a squared error. And of course the linear model is not the perfect, and it will not predict all the data accurately, meaning there is a difference between an actual value and the predicted value. The error is easily calculated by this. This is known as your residual. So we are comparing here the actual and predicted data. Here comes your hypothesis value, which is represented as y equals to beta naught plus beta 1 into x. Now, as proceeding ahead, we can see that there is a plot here. Now, this I'll explain you what exactly we are trying to achieve. This is the error equation which is used in regression, which is known as MSE value. What happens in this case is, let's say this is your regression line. Okay, this is your regression line. Anyway, let me explain you in the white where it can be explained better. You can write there and write there as well. Let's go to the whiteboard part. This is my writable pad where writable environment where I'll be setting up the things. Okay. So a quick overview of what the linear regression is capable of doing. Then I'll explain you where this MSE comes in here. Let it get opened. Okay. So I'm taking a simple example of a multi-class classification. Sorry, not multi-class classification. What I meant to say is that I'm gonna take an example of multiple input data, okay, and one target. Let us assume this is your multiple linear regression part. We have got a revenue here to predict. Revenue is dependent on number of click. So total number of click is, let's assume that the number of click is 10,000. The revenue generated is 700. When the number of click is 15,000, then revenue generated is 950. Revenue generated is revenue generated is 1100. Then number of click is 20,000. Next is revenue generated is 1500, and the number of click is 25,000. Here the revenue is represented as Y value, which is equivalent to initial revenue, that's beta naught, plus rate of change. Now in this case, the coefficient value represents the rate at which your feature will be changing. Okay, it is not about how the revenue will be. It will be showing that rate of change at which when your revenue will be changed when there will be a change in the number of clicks. So that is your rate of change. This is where the equation actually appears like this: y equals to beta naught plus beta 1 into x1. This is a simple linear regression equation, as I said earlier, because there is only one input and one output. But in real scenario, there will be multiple input and single output, which will be of continuous type. Now, if you will make a plot of number of click on a website or on a product with respect to revenue, it will be represented like this graph, and this is your regression graph. This is your regression graph. Here the plot that you are observing, it is representing a linear relationship between predicted output and independent scalar dependent variable. In this case, our predicted output will be there, and we'll be having scalar independent variable. So predicted output and scalar independent variable or input variable, which is represented by x. So we have on one side we have got the y value, on the other side we have got the x value. Now here comes the goal of the linear regression model. The goal of the linear regression model is represented now in a very simple manner. You need to understand that the goal of the linear regression model is to find the best fit line. Okay, out of all these combination, line number 2 is your best fit. Why? Because in this case the regression line is much more closer to all the sample data, and because of this reason linear regression model is considered to be the best fit line here, as you see. Further, let's talk about the residual. Now once the model is fitted and you see the residual terms, this is how the residual is represented. This is your actual value y1, this is your predicted value. All the predicted line or all the predicted value will fall over the same point. If your actual value and predicted value fall over the regression line, then there will be zero error. But if there is a slight difference between the actual and the predicted point, then it is represented as E1, E2, E3. You see that we are trying to compare. Now, if you see the difference between actual value and predicted value for y1, it will be representing it as a negative value, whereas between y2 and y2 hat, it will be a positive value, whereas the difference between y3 and y3 hat, it will be again a positive value. Y4 and y4 hat, it will be negative. Reason is very simple. Y4 is lower than y4 hat. Y5 is also lower than Y5 hat, so this will be also negative. Now if I follow a simple scenario of adding them together, now let's move ahead with our MSE values. Now, so that's the reason why we cannot settle for a simple summation and we can say that this is our total error. No, because if you will do the simple summation, the positive and the negative will cancel out each other. Instead, we have got mean squared error, which is represented as your cost function or error function value. And if you look at here, the cost function or the error function, it is represented as 1 by n I equals to 1 to n yi minus yi hat square. This is basically represented as your average value of the error. This is your actual value of the error, and it is represented as your cost function. This is called as MSE. Okay. Now this MSE has to minimize or it has to reduce. For that, the technique which is used is a very popular technique called as gradient descent algorithm. Gradient descent algorithm is in layman's term. First understand, then I'll talk about the maths behind it. The linear regression, or sorry, the gradient descent algorithm works in a very simple manner that it assumes this is your error curve. So as you see, this is your error curve, and the error curve that you see here, if you look at here, this is your error curve. In this error curve, there is a very simple thing. What you are expecting is that you have to minimize the actual minus predicted value. Oh, sorry, your uh, error has to minimize. Okay, now when we say that we have to minimize the error, what you will reduce basically. So this is your equation of the uh, error value, which is MSE value. Now let's expand this further. Okay, then you will get to know that what we are trying to minimize. So 1 by n is your number of sample. It will remain as it is, no change. Summation, okay, sum of all the value will also remain as it is, which will go from I equals to 1 to n. Yi is your actual value minus yi hat. This yi hat is your predicted value, and predicted value means we got here my beta naught plus beta 1 into x1 or beta 1 into x. We take the square of this. Now this is beta naught plus beta 1 into x. In this case, x is your input data, so we don't change much in the input value. It remains as it is. This is your actual value. Again, this will remain as well. This will also remain same. So actual value, you cannot adjust to minimize the error. Input data also you cannot adjust to minimize the error. Then what we are left with? Why there is an error? Error is because of the wrong value of these. So when the model is fitting, basically model is trying to train themselves to find the value of actual beta naught and beta 1, which is closer and closer towards the real value or the actual value, that will result into a model which will return you a perfect fitted model with a very less error or almost negligible error. So got to see here that we are comparing the actual value and the predicted value as well. Okay, now let's implement the gradient descent. Gradient descent is represented as beta naught nu minus beta naught older value minus alpha times of partial differentiation of error with respect to beta naught. This partial differentiation of error with respect to beta naught or partial differentiation of error with respect to beta is called as gradient. This is known as gradient. Del E by del beta naught. It's too light. This is known as gradient. This is partial differentiation of error with respect to beta naught. Okay, once we are trying to, now we have to minimize it. This new value we have to calculate by partially differentiating this older value. It also has this alpha value. Alpha is something which is called as learning rate, and learning rate will be the value between 0.001 to 0.1. This is the optimum learning rate. What happens when you try to implement this, and by what time or by how many times this will be iterated? So this will continue the process of minimizing the value, and assume that you roll a ball on the surface of an umbrella. That's exactly how the gradient descent behaves. It is going to be simply minimizing the error with respect to the beta value, and as you change, as it modifies, you see that there will be a steep drop first. So when the gap is large between actual value and the predicted value, there will be a steep drop in the error. At every point, it is trying to find out the tangent to the surface. What is this? Why tangent? Because this partial differentiation is nothing but it is considered to be a tangent to the surface actually. This is known as tangent to the surface. Okay, we are trying to calculate the tangent. Now here comes the goal, which is partial differentiation of error with respect to the beta value. This will continue to this point, and at this point your partial differentiation of error with respect to beta is 0 if you know the maths, because of the tangent. Tangent is tangent to the curve, tangent to the error curve will be flat. It will be 0. And if it will be 0, it will also mean that there will be no further update in these values. Correct? So that's how the things grow. This is how it will steep drop. Now, at every point of this ball placement is basically minimizing the total error, which is also known as your batch gradient descent. So what it does, it basically minimizes the overall value or sum of residual it try to minimize. It is not an individual error that it is trying to cater, but it just minimizes the overall error, and hence this is known as batch gradient descent. Batch gradient descent because it has to minimize the overall error. Okay. That's all. This is all about it. Just take a simple analogy. Gradient descent works in a similar manner or similar approach. When there will be the movement of the human being when he is going downward towards the towards the bottom of the mountain surface, as you see, when they will be at peak, they will show this type of response. They will take larger step and they will drop faster, whereas when they reaches here, this is where the goal is. This is considered to be the goal. So larger step, steep drop, and it will take small step when the steep is less. That's how the movement will take place. So this will also mean that the error will be minimized faster when the gap between the goal and the top peak is high. But as it will go down below, it will start decreasing at a very low rate, and it will stop when the model is already fitted properly. Okay. That's how the things are. This is where you have the initial weight of the model. There is initial value of beta naught and beta 1, which will give you the highest of the error. This is your highest error, and at every different point you will get a new value of beta naught and new value of beta 1, which will be updated by the rate of change. This is known as partial differentiation of error with respect to beta naught and beta 1. And what is this? In maths, this is known as tangent to the surface. So if this is your error surface, so you have to keep on taking the tangent here. This is your tangent to the error surface, and we try to minimize it. Okay, what is alpha here? Alpha is represented as learning rate. This is representing your overall error equation, which is represented as 1 upon n yi minus yi hat square. Okay, done, dusted, finished. What is the meaning of alpha? Alpha will decide at what rate the error will be minimizing. As you see in this case, so you see that when your alpha is too small, this will take more time to arrive at the goal, or you can also say more number of iteration will be required. When your alpha is too large, then learning rate, it will miss the minima. It may miss the minima point. It will miss the minima value. Further, alpha is your learning rate, which is just right. Alpha is your learning rate, which is just right. So here comes the error or cost function. Okay, any questions? Any questions? Any questions? In linear regression, there is any question? In d by d beta is beta, both. It will be beta naught, beta 1, beta 2, beta 3. All betas will be contributing. You see that beta naught will be updated, beta 1 will be updated. If there will be beta 2, it will be also updated. If there will be beta 3, it will be also updated simultaneously. And there will be a learning rate, which is fixed. The best is between 0.001 to 0.1. So add learning at a defined learning rate, this error will be this betas will be updated. Okay, so hope it makes sense. Hope you are able to understand them. Okay, looks like there are no questions, so we can go for a quick break. We'll come back to discuss the hands-on session on this using Python. 10 minutes break. Okay, let's get started with the linear regression example. Let me upload, I'll be uploading all these materials after we are done, okay, in the same Google Drive link. Meanwhile, let's start with our new Google Drive link. Let's start with a new notebook. So everybody started. Now we need to implement the linear regression model in this. Let's get started with our very simple example of linear regression. Let's start with a very interesting sample data, which will be about house price prediction. Let's do that house price prediction. Now, I'm not going to be making it a very simple, as you see in your maybe a YouTube video around. Rather than that, I'll be taking up a senior research scientist type of approach, and I'll be discussing about in that manner. First of all, let's just give it a name as a linear regression, and we start with our house price prediction. Okay, we will be making a house price prediction, and we need libraries like pandas, matplotlib, seaborn, and numpy and all. Let's just first import packages. When we start with import libraries or import packages, let's import the things as import numpy alias np, import pandas alias pd, import matplotlib, import seaborn. Further, let us split the data into train and test sets. We'll be doing it from sklearn. This is our split part. Okay, next is we need to import linear regression model. model and evaluation metric for scikit-learn package fee. It is started from sklearn. We are going for linear regression model. Now metric is mean squared error, R2 score, mean absolute error, and mean percentage error as well. We have to take that percentage error as well, mean absolute percentage error. Absolute value is basically also one of the metric that you can use uh, to find the metric value between both. Started with your imported part. Started. Say yes or no, right? If you're done, we'll be moving ahead as well. Now, once we have imported here, import warnings, filter warning. Let's read our read data set. We take here my house data, which is equals to pd dot read underscore csv, and the data set that I'll be taking up it from the GitHub link. GitHub is there with me. Let's take the datasets from all the list of the datasets which is available to us. From the list of data sets, I'm going to take house price data. Click on view. This is your data set. Let me provide you that. Provided you this data set. Display the head, which will be showing you the first 5 records. A lot of columns in this. Target is pretty much clear. Price of the house will be the target. Number of bedroom, number of bathrooms, square feet living area, square feet lot area, number of floors, waterfront, view, grade, square feet above area, square feet basement area, year built, year renovated, zip code, latitude, longitude, square feet lot, square feet living 15 and square feet lot 15. There are few things which will be hidden in between as well. Let me show you all the columns. For to show all the columns, we can use data frame dot columns, and it will show you the list of columns which are hidden. After view, there is condition of the house. That's it, which is hidden in between. Uh, Total overall column or rows. Let's try to see that through the help of shape function. Shape function returns rows and columns. 21,613 are your number of rows and 21 are your number of columns. Please start executing them one by one, everybody. Start executing them one by one. Import library, read dataset, show some important characteristics about the data, and then we'll start with the first part of machine learning is read dataset, and second step will be always about finding is there any missing data present in the dataset. You all please start from here and let me know. Now let's get started. Hope it is done till here and understood. The second step in machine learning is you have to implement data manipulation part, and it's about finding is there any missing value. Is there any missing value? It's pretty simple. Let's take here house data dot. Let's check for is null dot sum. It will show you there are no missing data in this. But as I told you earlier, this is not the perfect criteria to find if there is any missing data present in the data or not. To know is there any missing data present in the data set or not, you should first test through this definitely. But apart from this, you should also check with the info function. We have got house data dot info function, and it will return you the columns with stating that majority of them are numerical data. If there is a problem of missing data, you will see that a probable column, say price here, if somehow it is represented in D type as object, so you need to understand that there is some problematic thing in the data set. Okay, but if it is numerical, that means no issue. This is your test number 2 to find if there is a problem in the data set. Step number 3 will be about describe. When you see that majority of the column is numeric, straight away employ describe, and it will return you. And you see that you see a minimum value being 0 for that column, which cannot be 0. Like for example, bedrooms, okay, it can be 0. Bathrooms, it can be 0. But you cannot see that your price is getting 0 or your square foot living area is getting 0, latitude getting 0 or longitude getting 0. They cannot be 0 in realistic form, right? Yes, if there is no renovation found, then year renovated can be 0. Um, so one of the important criteria to check in the describe is the minimum value, and if data is suspiciously getting or is showing itself as a 0 value, so with that you can easily say that your price of the house is set to say this 7.5 e to the power 10 to the power 4. This indicates that your minimum value is this and not a 0. So if it shows that they are 0, it will mean that there is a problematic thing in the data set. Are there any duplicate rows? Let's check, is there any duplicate rows? Data manipulation is one of the important step here. We need to check is there any duplicate values. Once again, house data. To check the duplicate value, we know that we have learned about a function. It is known as duplicated dot sum. This is gonna return 0, which means that there are no missing data. Okay. Hope you have started executing them one by one from the link that I have shared. So we have tested no duplicate values. We have tested no sign of missing data. Great. Now time to test important thing in the data set, and that is this is not part of third part. This is basically a continuation of what we have started. Third part will be once data manipulation over, For linear regression only, we need to check for assumptions of linear regression model. Start with the linear regression assumptions of linear regression model, and we check it with is label normally distributed. We check it if your label is normally distributed. So we check SNS dot dist plot, and we compare if my house price data is showing the sign of normality. So one plot is dist plot. Okay, it shows that there is no. So what type of distribution is this? This is skewed, right? What type of skewness is there? Positive skewness, right? One big peak, one sharp peak. So kurtosis will be also very high. And so as you see that your data is showing the sign of so we have got this and you can also do KDE plot. That's also will do the same thing. It's kernel density estimator, and you have to just fill the color with fill to true. Read the packages, read dataset, columns, shape of the data. Is null.sum. Further, we have can see the info part. Further, we have got the describe part, and we check it for the duplicated rows. Let's go ahead with my KDE plot. Now, is it normally distributed? Let's test it. We will go for QQ plot, or you can also call it as quantile plot. We start with my SciPy. And here goes stats dot probability plot. And let me just also set some style as well. Set a SNS dot set underscore style white grid, and we have just given plt dot show. Now you look at here, this is your line, which is your perfect line. Or you can say this is your curve. This is not what we should expect if our data is normally distributed. In fact, this is the line which is your ideal line. And we expect that all our data sample should be close enough to this line. If your data sample is not close enough to this line, we can say that your data is not normally distributed. Let's check. So this is your quantile plot. Let's check it. with is there any outliers? Next thing to test is outliers. Yes, definitely there are a lot of outliers in this. PLT dot figure. Let's check the box plot for the data, which is house data. I'm going to take a square bracket of price. You see that this is how there are too many outliers in this data set. We are able to find out that there are too many outliers. We need to handle them. Let's handle the outliers. We are having handling the outliers part. Let's start with it. Def. We take here we'll feed the data and the column name both. Let's calculate IQR. Lower bound followed by upper bound. And let's calculate the outlier value. But instead of showing the outlier value, let's just get the row indexes value of these outliers that matches in the data set. So this is how we do. Okay, we got it. This function, you can use it for other data sets as well, because this is just a function and it is gonna be providing you the response as you see. Now let's take here my outliers, which is your interquartile range, and let's just provide the sample data, which is house data and price of the house. And there is some problem here. Let me just check. Yes. Instead of getting data, you should have this. So it is going to return you the indexes. Return index of outlier value. Now there are too many outliers in this. The ideal scenario of handling the outliers are three. Replace outlier by any mean median, replace by median value, replace by return indexes of the outlier part. These are all your indexes. Followed by, now there is one more thing that you can do is you can set up the cap. So let's handle the outlier by capping the maximum value. What we'll do, instead of replacing the missing data by median value, or the other option is we can drop it. Let's just cap that lower value will be, the lower limit will be lower bound and upper limit will be till upper bound. So any value exceeding the upper limit will be restricted to that cap. Let's just copy paste all these four lines. Let's replace data by the data house data, and column we are targeting the price, because price has to be converted into normal distribution, and from the price only we have to handle the missing data. Let's handle the outlier by capping. Handle outliers by capping. No, just let's replace the price by, let's apply clip. Let's just clip here our lower limit. So any value which is lower than the lower limit will be set to lower bound, and the upper value will be set up to upper bound. Done. Okay, let's check what happens when we have implemented the clip. That is, we have bounded all these outliers to the upper bound part. and hence what you receive is a quite a nice distribution of the data, which is quite closer to the normal distribution as well. More interesting thing is that there are no outliers. Okay, let's see what happens to our normal distribution part. Let's see what is the price looks like. So after handling the outliers, the peak is now a little broader. There is nothing like an idle scenario, but because if there will be an idle, we will get a very high accuracy as well. So you can see clearly that your model is fitted. It's not that this peak is indicating that lot of samples, all those outliers. Now let's move ahead. There are still a little skewness, but not that high. Next part is very important. We need to check for the second assumption is, first assumption is that your target should be normally distributed, which we are eventually able to make it after handling these many outliers. Let's go for the multicollinearity part, right? We have this multicollinearity thing as well. If you remember, is there any multicollinearity? And for that, we have got multicollinearity. Is there any Let's go ahead. Now from stats models dot stats dot outliers influence, this stores the variance inflation factor. So let's just import here variance inflation factor, which is your VIF value, and this is the ultimate test or measure to check if there is any multicollinearity between the features value. X equals to house data. Let's get a drop. Let me also drop two more not so important column, and that is ID. Now let's get a VIF value. Let's calculate it for all the columns. We take a feature value with x dot columns. We got a VIF value. Now we have got a feature here with respect to the VIF value. Now we need to check here that few VIF is going towards infinite value, that is too large. And even if forget about that large value, you see that longitude, this is 10 to the power 6. And if you see the latitude, that is 10 to the power 5, zip code 10 to the power 6. Those are like really high numbers. So there is a plenty of multi-collinearity. These features are not independent from each other, okay? The reason why I have dropped ID and date, pretty simple to understand that these are unwanted columns for prediction of the price of the house. ID is just a, purchase ID kind of a thing, and date is also useless in this because we are not solving for a time series data. Only in time series, date is considered to be a good feature. For else, it's not at all required. Why now? You might be wondering why price is eliminated, because see, we are targeting only the features part. We are not looking for other things. Now start with my features and target value. Let's continue. X equals to house price data. Let us remove all those columns except which are not required. So from the house, we have to remove ID. We have to remove date column. We have to remove those all high VIF value columns, like let's pick square feet above, followed by square feet basement. So square feet above, square feet basement, square feet living area. These are all very high values, followed by zip code, followed by the longitude. Out of latitude and longitude, I'm just removing one, and the other one I'm keeping. The target value, that is y, is your price value only. So that's too many features. Out of that, we got rid of all those features which are showing the sign of multicollinearity. And how did I tested that multicollinearity thing? Through all these values. Okay, so those I kept latitude here because let's be logical here. We should have some understanding like what type of data we are targeting. We are targeting the we have to keep few data here. X train. We start with my random state equals to 2. We split the data into train and test. Now in this, we have got a random sample, a random state as well. Okay, this is about a random sample, the data into train and test sets, followed by we have a test size which is 20%, which also means that your training size is or training sample size is 80%. Let's just also pick here my random state equals to 2. This random state is important because this ensures that the split is, why to fix the random state value? This is to ensure that the split is reproducible. Okay, next let us So after splitting the data into train and test, 80% of the data will be used to train the model. Now let's go for my data pre-processing part. Let's implement a standard scaler. Let's go ahead with my fit part. Now, what are we trying to do is we are trying to fit as per the scaling part, we are fitting as per the training data, and then we are making the transformation part. This is to standardize the sample data. Standardize the features using standard scaler, which basically transform the data and which standardizes using standard scaler. Now, why it is important? Because remember that we are implementing linear regression, so this is important. To ensure models that all features are on the same scale, and it is used to improve the performance of the statistical model. Okay, we transform it. Reason why we need to transform is that we need all our data should be in the same scale. Now see here in this case, Why it is important to do this part? Look at this X train data. Now, if you look at here, and in fact, let's just take your X value. See, in this case, the values that we have selected, these features, they are having different range. Bedroom, it is in the units range. Bathroom, again unit and floating value. Square foot lot area is in going from few hundred to even 10,000. Floor unit, waterfront unit, view is again unit, condition is again unit, year built is again in 1000, year renovated is 0 and 1000 part, latitude and longitude, latitude is in tens places. So there are differences in their scale, they are not in same scale, and it is recommended that if you are performing a regression example, all your features should be in the same scale, which means that if you will see the X train data, now they are in same scale. Look at them. Everything is in the floating term. They are not deviated much from each other. Okay. What does it uses? It uses Z score, which is X minus mu divided by sigma. That's the formula it uses. So it uses Z score formula to transform your actual data. To transform actual sample to transform sample data. Okay. So it's near of the, it is required in linear regression model, and without this the model performance may get down. Okay, so if you will apply on the original data set, your accuracy or the performance of the model will be little dipped. Now let's go for linear regression finally. Now we are ready to implement the model. So see, the point of machine learning training is that you are not training, we are not actually learning about how to train the model, but more than that, 80% of the time is spent on data preparation, which we have done, and I'm sure I have showed you some of the highly refined technique which is used in the industry, that how you prepare the data, how to handle the missing data, how to handle, how to handle the outliers. We have learned how to make your target go normally distributed, that is what we have handled. How to apply data pre-processing also we have handled. Okay, and these are important terms. And yes, how to handle the multi-collinearity between the features is also we have learned. Now everything is ready. Let's just take a regression model followed by your linear regression model and fit your model. Let's get a score X train on Y. Now to test the performance of the model, we take a score which is X test scaled. Oh, we have transformed it to weight. This is bad. Should have been scaled. This should have been also scaled. Pyramid. Y train will remain as it is. Only changes will be in X train. And now that we have that X test scaled and Y test as well, so we get the score. It's coming out to be 74.13. This is one of the metric. Now, do not get confused. This is not accuracy. This is R squared value. This score is not accuracy value. Okay, this is R squared value, which is basically represented as coefficient of determination. This tells us how much of the target variability is explained by the model. Variability is explained by the model. This is your coefficient of determination. This tells us how much of the target variability is explained by the model here. So let's get our eighth part, which is regression metric. Let's just check it. We have got y predicted outcome, which is represented by a linear regression model. Predict the output. Get our R2 score followed by y test compared with y predicted value. This is your R square value. That's the performance of the model. Now this R square value range is between 0 to 1. So if it will be closer to 0, R squared range between 0 and 1. The more and more this R squared is closer towards 1, better will be your predictability. And if it will be closer towards a 0, model will be let's go. We start with the mean squared error. Let's compare your actual value and predicted value. Huh? Okay, we got here my MSE value followed by mean absolute error. Now, the error value, I don't have to tell you, this should be as low as possible. Next one is RMSE value or root mean square error. Just take the square root of MSE value and print RMSE. Lower the better. Similarly, mean absolute error, lower the better. And last one, MAPE value, again, mean absolute percentage error, lower the better. So these are all your different type of metric. Out of that, R square is the best metric to first check, because this will tell you how well your feature has able to explain the variability between the actual value and the predicted value. Now this is your regression plot. That's your regression line. You can see how well it is fitted. These dots, they are your outlier, so you can ignore them. Rest all quite good. Now let's make a prediction for new sample data. New sample prediction. Let's take a new sample data. Xtest dot sample data. We have taken a sample data and let's scale it. So we are transforming it. We need to transform your original sample data, remember. And let's make a prediction with model dot predict x sample scaled. What is model? Now this is your predicted price of the house for this sample data. Remember, every time you will be executing it, your sample will be different. So do not expect the same result. But yes, this is how you can take it. You take a sample data, you need to scale it, and you predict it through the model directly. These are your, this is your Excel sample, 8584. Okay, everyone, we're done here. That's it for today's session. Any questions? Thank you, everyone, for joining today's session. Tomorrow we'll start with logistic regression as well. Bye bye.